So this is your bad luck, but about half of the class was away when the course finished. You blinked and it was over. So, everything I did in the whole semester culminates in this formula, which is called a trace formula. I call it classical, and it's totally amazing. After all the, pondering how the topology of the space works, what a stability of local orbits, etc., thinking of Perron-Frobenius operators, density evolution operators, all kinds of fancy stuff. Bingo. A beautiful, simple formula, whose meaning is that on the left-hand side, the world is full of periodic orbits. If we have an ergodic system, an unstable system, and they have some complicated topology in the state space. So here is one of them. And they all live in state space. And if things are nice, the state spaces are densely filled out. And so in every neighborhood, open neighborhood, there are periodic points belonging to periodic orbits. And the idea of this thing was, when they're unstable, this periodic, actually also when they're stable, but when almost always periodic orbits are isolated unless they belong to continuous families. And that we took care of by quotienting spatial symmetries. So they're almost always isolated. And why they're isolated? Because they're hyperbolic, meaning that anybody in neighborhood, is being shoved away. So it's impossible to have a recurrence in a close neighborhood because things get sucked in, thrown away. So each periodic orbit of some period doesn't have a neighbor of the similar period, but it might be a much longer periodic orbit that went someplace and came back to the neighborhood. But for a given time, we can put a little tube around each orbit. So I can write a little tube. So there's just an open neighborhood of this periodic orbit, which has a property that there is nobody else in this little tube who is exactly recurrent. And then the way that this was evaluated was to say, when I look at this tube, it has a natural coordinate system. So when I blow it up a little bit, and easiest is to put a Poincaré section. So this tube cuts the Poincaré section here. Inside there is a periodic orbit, which on Poincaré section has a periodic point. And it's totally natural to construct coordinates, one of them which is parallel. So it's coordinate that goes along the tube, and it's a cyclic one because the periodic orbit itself is finite period. So if I put some coordinate here, and then the rest, we'll call it transverse. And for periodic orbit in arbitrary dimension, you can always decompose this locally. And the way then we did these calculations, we showed that integration, and I haven't actually done it, but it's in the book. I've done it only for the maps, I've done it for transverse part. But for longitudinal part, you show that morally, the length of this tube is actually its period. So this thing that used to be counting how many periodic points we had when we were computing trace maps of transition matrices, very simple finite dimensional matrices, there's always number of points because each periodic point contributed to trace. In continuum, that just becomes a continuum variable, and dimensionally turns out to be time. So this is the length. And then the transverse one is the one that we did when you blinked last Thursday. But basically, in transverse direction, what happens, you have to integrate Karan-Frobenius operator, which says I have to integrate transverse part of the delta function of starting at x and ending at x, being on periodic point. So this is our transverse coordinates. And that this gives me 1, d minus 1 dimensional. This one is d minus 1 dimensional. And this part gives me the matrix intersections, a transverse matrix. And I'm using a new letter. In mathematics, they have something called monodromy. It's from the Greek dromos, the stadium, and mono, meaning once. So it means you go once around the play field or something. So that's monodromy. And this one is hyperbolic because we have removed the marginal direction here. So this one has eigenvalues which are either larger or smaller than 1. And then integrating high-dimensional Dirac delta function always produces a Jacobian. You have to go into coordinates where this vanishes, and that's this Jacobian. That's all. And then our evolution operator had 2 pieces. One was we computed something on periodic orbit because we were developing field averaging. And this is integrated observable on the periodic orbit. And then there was a cost which came from Laplace function, Laplace transform. So that's it. On the left-hand side, we had this. Where did this come from? This came from a Laplace transform. We wrote the evolution operator at time t as evolution operator for infinitesimal time integrated. So you can think in quantum mechanics, this is like Hamiltonian. It's not quite right. And then Laplace transform of this gave us 1 over S, where S is a Laplace transform variable. It's dual to time, just like energy is dual to time, minus operator. So Laplace transform gave us a resolvent. And I'm willing to discuss all these things after you have watched the videos. And if you don't understand something, put it on Piazza. I will dutifully answer to all questions. But this is testing. Imagine that you're part of 40,000 people who will no doubt want to take a course like this some later time. And trace of this object is the sum of the eigenvalues of the operator. So that's the left-hand side. So what this means is that on the right-hand side, we look at our world and we divide it in little local neighborhoods, and on each one of them, we have a formula to compute contribution of recurrent solution. So it's because of this trace formula that we are forced to look at periodic orbits. It's hard, I don't enjoy it, but I don't think we have any choice. This is the natural invariant set. This Jacobian is, as we showed very early in the course, it's invariant under all smooth coordinate transformation. So it doesn't matter whether you do it in Marburg or in Kyoto, this determinant will always be the same, even though the matrix might look different. The eigenvalue is always the same. Periodic orbits are indestructible. They're topological invariants. Whoever finds a periodic orbit any place, it'll exist in any other realization, any other coordinate version. If you agree that we are measuring an observable, we all get the same answer. It's very simple. You just integrate whatever you're looking on the trajectory. So it's very simple to compute. We'll all agree more or less what the period is. That might be open to discussion if you redefine the time, but then you'll have to think about what it means on the left-hand side as well, because it shows up on the left-hand side.